Okay, just to recollect what we have done yesterday, I mean last class. So, relative humidity was defined as the moisture content by saturation moisture content, and we said that we can calculate this out using some empirical formulae. So, the empirical formulae, one of the empirical formulas, there are people are trying to, basically it is the same psychrometric chart, fit them into equation and get some empirical formulae. So, one of them is like this: partial vapor pressure, partial vapor pressure, partial vapor pressure. Okay, the pen has to be activated. Partial vapor pressure is a function of PSV, some constant. P0 is the atmospheric pressure, T minus TW, right? And PSV, this is calculated from this empirical formula. So, this is only wet bulb temperature, right. So, this is depends upon wet bulb temperature. This is atmospheric pressure, and this is, so this constant actually depends on wet bulb temperature, and this is anyway a function of wet bulb temperature. So, vapor pressure is a function of wet bulb temperature, right, and difference between wet bulb temperature and dry bulb temperature. So, that is what is taken into account. Okay. And then saturated pressure, because we would need to calculate out GS also. So, when we want to calculate out saturated pressure, PS, this would be given, this is given by this formula. So, instead to replace this, you get PS actually, saturated vapor pressure, right, and PS is what saturated, is at WBT corresponding to WBT, this one, and PS is a saturated vapor pressure at the dry bulb temperature. Now, GGS is nothing but 0.622 PV divided by minus PV, right. So, this if we know the PV's vapor pressure, this we know, then we can find it out, right. So, but relative humidity we can find out actually. So, that is how we find out, right. So, okay, moisture content G divided by this, divided by, it would be divided by, this is only G, this part is only G, and GS will be how much? Instead of this PV, it will be now saturated vapor pressure, which we will find out using PS, right. So, the relative ratio of these two will give me the relative humidity. Okay. So, psychrometric chart anyway I have talked about, and one may a little bit look into some equation of dew point, because if you want to estimate out how much condensation or what is the temperature, supposing the moisture content corresponding to dew point you are interested for a given condition. So, that you want to reduce down the moisture content, you would like to know the information, or you would like to have the knowledge of dew point as well as wet bulb depression, just some ideas related to that. Some of them would be, for example, one is calculating the relative humidity that I have just mentioned earlier. Then dew point you want to calculate it, there is some empirical formulae. But before that, let us understand a little bit more. If this is the rate of moisture flow, moisture vapor flow, that would be depending upon the gradient of concentration, right, fixed law, and this is the diffusivity or diffusion coefficient, right. So, I have got let us say liquid water and surrounding air is there. So, vapor molecule will actually depending upon the concentration, because at the liquid concentration is 1, and if the concentration is low, so there is a concentration gradient existing. So, moisture vapor will flow. So, wherever there is a concentration gradient, the molecular diffusion takes place. So, we can actually use this same formula, and what is concentration here? Concentration, because it would depend upon, concentration is nothing but mass per unit volume, right. So, mass per unit volume, if you remember, mass per unit volume, and mass divided by mv is nothing but n, right, n. So, PV equals to nRT, so I can replace this V from here, 1 by V would be P by P by so m by b. So, this would be simply m by mv. So, P m by b will be P m b divided by R T, P m b divided by R T, because P is equals to P b equals to m R T by m v, where this is the molecular weight of the vapor. So, m by b is the concentration, can be written in this manner, right. Therefore, dC dx will be dPb dx, dC dx, C is nothing but this. So, mb I can these are all constant except the Pb. So, partial pressure partial differential of pressure, this is, and C is nothing but R by mb, R by mb is the C. This was universal gas constant, this is the specific gas constant for the moisture vapor. So, you can have, and then it will be related to this. Okay. So, m dot can be, combining this two equation, we get m dot in this manner, and there is a friction coefficient you can add, mu is a friction coefficient you can add, right. So, this from law of convection, or you can, delta P b is nothing but P s v minus P v, saturated vapor pressure at the water surface, close to the water surface, minus the vapor pressure existing at some distance. So, that is this one, this part is nothing but this one, right, and all this we can put in terms of a coefficient, vapor transfer coefficient, convective sort of vapor pressure, which depends upon the vapor pressure difference. C t remains. So, H divided d by mu can be is something like H d, right. So, d by mu is something like H d. So, therefore, one can express this rate as a difference of pressure, vapor pressure difference, saturation vapor pressure near the surface and the vapor pressure of the air away from the water surface or water body, depending upon that one can express in this manner, right. So, if I want to find out latent heat transfer corresponding to this, simply multiplied by L, right. Now, T minus T w is a wet bulb depression, will be how much? This is the amount of heat transfer. So, actually you see the heat is taken from the, basically if I supply heat. So, H this T minus T w, H into convective T w exists near the surface, wet bulb temperature is near the surface, away from the surface it is dry bulb temperature, because it is fully saturated near the water body where the evaporation is taking place, let us say skin or wherever it is. So, there is the wet bulb temperature will exist where it is near. So, the heat transfer is given by this convective heat transfer, heat comes because of convection, air and near the surface water body or whatever it is. So, this is a H T w must be equals to this, H T w must be equals to H d L P s b. So, if I combine this, I get an expression for wet bulb depression, H d by H, where this is convective heat transfer coefficient, L, etc., etc. So, this is what is. So, wet bulb depression can be theoretically calculated knowing the temperature, right. I just forgot to mention earlier that the C1 that was there in that empirical equation related to relative humidity, this earlier we discussed about this one. These values are given for, these values of C1 etc. are given for type of hygrometer you are using, or type, these values are available with us. These values are available with us, values of these ones are available with us, this is anyways given. So, this constant has to be given. Similarly, this constant would be known to us, this constant would be, this values constant etc. has to be known to us. So, what is dew point? Dew point corresponds to, this is, so anyway this is T w, and the H d by H can be related to increase in, this can be related to rho into specific heat, H d by H can be related to rho into specific heat, because that is the amount of, this is basically sensible heat transfer, and latent heat, this is latent heat transfer, the convective heat transfer was sensible heat transfer. So, if the density and specific heat of this one is known, this multiplied by T, this multiplied, this can be H d by H can be related to rho Cp. Okay. Now, dew point, there is an empirical formula like this. For dew point, there is an empirical formula like this, This is 4030 T temperature plus 235 and T ln phi, where this is a phi is a relative humidity plus minus 235. So, dew point temperature, this is an empirical formula from which you can find out. So, these are some of those equations which can be used to to find out the relative humidity from wet bulb and dry bulb temperature I have said, and for a given vapor pressure or saturation vapor pressure or given temperature, the wet bulb depression corresponding to PSB PB, or in other words for the relative humidity also you can back calculate out. So, what is the wet bulb depression you can calculate out, and this dew point one can calculate out if required. So, that is what it is, right. So, let us look at an example. Say from psychrometric chart for atmospheric pressure of this, the following values are obtained. This is just an example to understand the use of the empirical equation to find out relative humidity rather than moisture content rather than psychrometric chart. So, what we are doing from the psychrometric chart atmospheric pressure, of course, we know following values are obtained: wet bulb temperature 15 degree, dry bulb temperature 28.9, relative humidity is 20%. Now, use equation, those equations that I was talking about, and substitute wet bulb temperature and dry bulb temperature. You can find out P, saturation vapor pressure, etc., PS saturation vapor pressure, and P of the vapor PV that I was talking about. So, you can, the value you will find out is by, if you calculate. So, this is from psychrometric chart you get 20% as the relative humidity. Use the formula, just check it yourself. You will find that PS value is this, PV value is this actually, and you calculate out phi value, it will turn out to be 0.199. So, error is about 0.2%. This, so you can validate this by calculation. You can validate this by calculation whether this is matching or not. From the psychrometric chart for this dry bulb temperature, wet bulb temperature, this dry bulb temperature, relative humidity is 20%. If you use the formulae, you will get about 19.99% and all that. So, you can check this, usually error is small. Now, specific enthalpy, I stated it, and maybe I have given a formula earlier. This is given by this formula, Cp into temperature, because we take the temperature 0 degree centigrade as a datum, and this is the specific heat of water vapor into temperature plus latent heat, and this is the moisture content, right. This is the moisture content. So, this I have mentioned earlier. So, cooling load, when you want to calculate out, you can use this formula, right. Okay. So, that is it related to example problem and relevant equations related to calculating the supply air moisture content, quantity of supply air you need, and temperature differential. Anyway, we pre-decided based on the decisions, how we decide about that. We have discussed this, and based on how much is the amount of heat you would like to remove, both sensible and latent heat. So, therefore, if you if for example, you want to decide upon, first of all, if you want to decide upon for a space, find out the design latent heat to be removed and sensible heat to be removed. It is a design condition, because capacity is based on design condition, not the detailed load, that would be different. Detailed yearly cooling load, then you have, because that would vary from time to time, but capacity is based on design, right. Now, first level of how much supply, what air supply you require, and what is this condition, that is to be found out. Once you have found out that for this room, another room, etc., diversity factor can be applied to find out the system that would actually supply this air. The mechanical system, of course, basic, some very simple basic principles we have discussed, but there are many modern mechanical systems that is there for refrigeration part. That that of course we don't know. You might select from the market or discuss with mechanical services engineer to select which one is the right suitable for you. So, that kind of like it would help you to make decision making related to HVAC, but as such HVAC is a it could be a something like it's a full subject, maybe spanning around 2-3 courses. So, we try to give a nutshell the kind of introduction to this one, and what is required from a building services engineer's point of view, at least the information that is required, where you can take part in decision making.